Hello everyone. I'm going to talk about lower bounds on regret for noisy GP bandits. So this is a joint work with Jonathan Scarlett, who unfortunately couldn't be with us here today, and with Volkan Chever. So in the first part of the talk, I will mostly talk about the setting itself, and in the second part of the talk, I state our main results. So in this work, we are basically interested in maximizing some unknown function f, for which we assume that it is also expensive to evaluate. The only way we can learn about this function is through noisy evaluations. So basically, we can query the function at some x and observe a noisy observation y. In this particular work, we assume that the noise is Gaussian. We also assume a sequential setting, which means that at every time step t, we basically choose a point in the domain based on all our previous decisions and the corresponding observations. This also corresponds to the bandit feedback because we only observe noisy sample of the selected point. Now, this problem is present in many applications nowadays, ranging from automatic machine learning to environmental monitoring, sensor networks, recommender systems, and so on. The problem itself is hard in general without any further assumptions. So in this work, we are going to assume that the function itself exhibits some sort of smoothness. I'll get back to this in a few slides. We also need some meaningful success metric, and for that one, we're going to use regret, and in particular, two notions of regret, simple regret and cumulative regret. So let x star be the maximizer of the function, then simple regret, the idea is that after t rounds, we just report the point x bar, and the simple regret is simply the difference between the optimal function value and the function value evaluated at the point x bar. When it comes to cumulative regret, it's simply a sum of the regrets that we incur at every round, where this xt represents the point that we sampled at time t. Now, in GP bandit optimization, people usually model the unknown function as a sample from a Gaussian process with some mean function mu and a known kernel function kappa. And depending on the function that we want to model, we can use different kernels that basically dictate the smoothness of the function we want to model. So two most widely used kernels are squared exponential kernel and Matern kernel. They're both isotropic, meaning that they depend on the distance between the points, and they also depend on some hyperparameters such as length scale and this new parameter which further dictates smoothness. Now here are a few samples from a GP with squared exponential kernel and a few samples from a GP with the Matern kernel. Okay, so in GP bandit optimization, we distinguish between two approaches. One is the one that I already mentioned. It's a Bayesian approach where f is being drawn from a Gaussian process. And the nice thing about this is that conditional previous samples that we obtained, we can still compute the posterior in a closed form. And there exist many, because the posterior essentially remains Gaussian, and there exist many algorithms such as expected improvement, upper confidence bound algorithm, entropy search, that basically exploit the knowledge of the posterior to choose where to query the function next. Now, in the non-Bayesian approach, we assume that there's a kernel function and it induces the reproducing kernel Hilbert space. So here we are going to assume, in this work in particular, that the unknown function has a bounded RKHS norm. So in this work, we are going to consider the non-Bayesian approach. A nice thing about this non-Bayesian approach that these posterior updates and the before mentioned algorithms, they still probably work in this setting. So one advantage of this setting is that it puts less faith in exact prior distribution. Now, in the previous works, people looked at the upper bounds on the regret, and especially in Srinivas et al., they provided an upper bounds for the cumulative regret for GPU-CB algorithm, and some authors also looked at lower bounds in the noiseless setting. But to our knowledge, no one has considered lower bounds for the noisy setting. So this work is about lower bounds on both simple and cumulative regret for non-Bayesian setting, the setting where we assume that the unknown function has a bounded RKHS norm. Now here are our main results. So for the squared exponential kernel, so let T, capital T denote time horizon, T is a function dimension, and epsilon is the target simple regret. We here present the upper bounds, the existing upper bounds, and the lower bounds that are obtained in our work. and for both cumulative regret and time to achieve a simple regret of epsilon. So now, if we look at the upper bounds and their corresponding lower bounds, we can see that these two coincide up to the factor of 2 in the exponent. So here we have 2, and here we don't have 1. So when it comes to this, we see that our lower bounds nearly match the existing upper bounds, and we conjecture that these upper bounds can be improved and that our lower bound is tight. Now for the Matern kernel, we have this additional parameter nu, and here the gap is more significant between the existing upper bounds and lower bounds in both cases. So if you look at the upper bound for the cumulative regret, this one is not sublinear for every value of parameter nu and every dimension d. So on the other hand, the lower bounds is always sublinear in terms of t for any parameter nu and d. So we believe that analogous upper bounds, the same ones as our lower bounds, are possible with d times d plus 1 instead of this d. But still, we don't have a proof for this. Now let me just give you a brief intuition about our proof. So this is the main idea. So we construct a class of needle in haystack type functions. So if you look at the following illustration, we have a finite set of functions, 5 of them in particular here in this image, and each of them attains its maximum at value 2 epsilon. So each of them is also parameterized by this width parameter w. So our idea is to pack as many functions as possible here, and in order to get the better bounds, but which means that we want this w to be as small as possible. But on the other hand, we can't allow this w to be a small, arbitrarily small, because that would violate the RKHS norm bound. So a very important feature of this construction, yes, so we basically need to carefully choose this w. Very important feature of this construction is that any point in the domain is only epsilon optimal for at most one function. Okay, and now if the true function, the true underlying function that we want to optimize is uniform on this finite set of functions, then the problem of simple regret not exceeding some amount, some value epsilon, is basically equivalent to identifying the correct function index. Moreover, we use the fact that the worst case regret, when the true underlying function is any of these functions in the finite set, is lower bounded by the average regret, where average is taken over all possible functions in the set. So this is the main intuition behind our proof, and the main mathematical tools that we use basically combine the RKHS norm bounding techniques and some techniques from some regret bounding techniques that are borrowed from the multi-arm bandit literature. So for more questions about this, please come and visit our poster. Thank you.